Okay, let's take a look at questions 7 and 8. In question 7, we drop a ball from rest and it falls to the floor. And it starts out with an initial potential energy of 10 joules. It hits the ground, it bounces back up to a height where the potential energy is only 7 joules. So clearly there's been 3 joules of energy lost, and that is lost because of the contact between the ball and the floor, vibrations that set up in the floor, vibrations that set up in the ball, those kinds of little micro kinetic energies with lots of particles kind of carrying away what we might call thermal energy. So the question is, what was the mechanical energy of the ball earth floor system the instant the ball left the floor? First of all, let's define mechanical energy. The mechanical energy is the sum of the kinetic and the potential energies at any given moment. And we see that definition right here. Just as it leaves the floor, the contact time with the floor is over and some of that original 10 joules has been lost to thermal energy. So the mechanical energy of the system is simply 7 joules. We're told that that it eventually reaches a height of 7 joules. So once once the ball leaves the floor, there's no more like loss of energy until it hits the ground again. So the exchange of potential and kinetic energies will go on as we've seen many times before. So just as it leaves the floor, the potential energy is essentially 0. The kinetic energy must be 7. Even if we don't know exactly what the split is, what we know is that it jumps up off the floor and reaches a height where the potential energy is 7 joules. So that must be the mechanical energy, the sum of the kinetic and potential energies throughout that sort of second bounce. The only other thing to say, I think, about this question is the ball earth floor system sounds kind of unnecessarily complicated, but they're basically wanting you to think about the idea that there is a floor that's involved here, and that floor may absorb some of the energy, but it doesn't participate in any of the mechanical energy ideas. So while the total energy of the ball earth floor system is still, say, 10 joules from originally, the essentially in this case only the ball takes part in the calculation or the thinking about mechanical energy. So that's a little bit of a tricky question there that depends upon your understanding of mechanical energy. All right, let's take a look at question number 8, just on the other side of the page here. Let's see if I can open that up. There we go. Okay, so here's question number 8. This is now probably a little bit more familiar to us than it was a couple of weeks ago. We've got a spinning disk that has an initial angular velocity of omega 0, and then there are these two forces that are acting on the disk. One that is operating on the right-hand side of 40 newtons, one on the left-hand side of 20 newtons. If it was just this 20 Newton force, the disk would continue to spin in this counterclockwise direction, and in fact would pick up a greater angular velocity. If it was just this 40 Newton force, then the angular velocity would slow down and decrease, and eventually, if that force persisted, we'd start getting the disk to spin in a clockwise direction. In either case, we can identify the torque as a force times a distance, and the reason I want you to look at that is that the resulting torque can be kind of compared by just looking at forces, because they're both acting on the outside of this disk, which we assume to be a circle, and so the distance from the center is the same, so they have the same torque arm, but of course one force is larger than the other. Okay, so given that, we can anticipate that the competition between these two forces and the resulting torques will be one where this disk must be slowing down, and if this continues, it will eventually reverse direction and start spinning clockwise. Now, we're told counterclockwise is positive. So what we're looking for then is a graph that starts out positively and decreases, goes through zero, and possibly becomes negative. So that's not happening here. It's the exact opposite of what we're looking for. In selection B, we've got constant negative velocity, angular velocity. Then finally in C, we can see that it starts off with omega 0, decreases, goes through 0, and can become a clockwise torque. So selection C is our choice. All right, we'll take a look at questions. Let's do a little preview here. We'll take a look at question 18 in a few minutes. Thanks.